G'day chemistry students. In this video, we're going to be looking at dot points 3.1.1, 2, and 4. And we're going to be starting to look at representing a lot of the chemical reactions that we're going to be working with in this module. Now, to do that, we're going to be focusing on combining some of the skills and techniques that we learnt over the first couple of modules. Now, the first one is all about balancing equations, taking formulas or written formulas that are written up in an equation and making sure that all of our atoms are balanced, or the counts of atoms are balanced based on the law of conservation of mass. What we're also going to be able to start working on doing is taking a worded problem or a worded description of a chemical reaction and taking all of those worded formulae of different kinds of chemicals and writing them down as a proper form of chemical formula that's required for writing down a balanced equation. Let's get started. Now, what I'm going to be doing first is looking at how to name a lot of the chemical formula that we're going to be working with. So imagining that we've been given a worded part or a worded name of the formula, then turning it into a formula with chemical symbols so that we can then start to look at doing some practice questions where we can balance the equations. What I want to look at first is how to name an ionic substance. So in an ionic substance, you'll be given the name of the cation, you'll be given the name of the anion, and you'll have to put them together to make sure that the charges are balanced to write down a correct formula. So let's go through the process step by step. Now, when you're given a cation, what you're going to be given first is the name of the cation or the positively charged element. So what can happen is you could either be given a cation that comes from the S or P block, a metal from there. You might be given a metal from the D block, or you might be given the metal from a cation that is a polyatomic ion. Let's go through each of these examples to try and figure out how to write their formula and their charge. So first one, we're looking at magnesium, which belongs in the S block. It's right here. It's in column number 2, which means it has 2 valence electrons. Knowing this, we can figure out its charge. So what we know is that magnesium atoms that don't have any charge have 2 electrons on the outer shell. Now, what it can do is to stabilize its electron configuration, either gain 6 electrons to make 8 on that outer shell, which it's quite happy to do. It would be quite happy to do because it would be stable. But the easier alternative is to get rid of the 2 electrons that are there, which means if we're getting rid of 2 negative charges, the charge of the magnesium would be positive 2. Other examples, if we were to have sodium here, Na, with 1 electron on the outer shell, easiest thing for it to do is get rid of 1 electron, which means it would have a charge of +1. Boron, another example, would have a charge of +3 because it gets rid of its 3 outer shell electrons. If we were given a D block cation, so for example, copper, it sits here, number 29 in the D block. It doesn't sit on the S or P block, so there's no patterns for the number of valence electrons that it has. In fact, copper can sometimes either get rid of 2 or get rid of 1 electron to become copper 2+ or copper 1+. So if you're given a worded equation, the way that you determine the charge is by the Roman numerals that are provided. You can't just assume what the charge of copper is. You have to be told, otherwise you can't solve the problem. So if it was copper 2, for example, it would be copper and then in brackets 2 written in Roman numerals, which means that the charge of this copper atom here, or this copper cation, would be 2+. Now, the other, and this one's quite rare, the other kind of cation can be polyatomic. So, for example, ammonium is a polyatomic ion and can be found on a table of polyatomic ions like the ones that we've used in class before. Now, this is something that you don't get in exam conditions. For HSC, for trial exams, for yearly exams, etc. It is something that you're going to have to start beginning to commit to memory. So we have a table as a reference when we're working on problems in class, but it is something that you are going to have to start memorizing in some way, shape, or form. But if we look at the table of polyatomic ions, we'll find that the formula for ammonium is NH4 and its charge is + or +1. Now, if we start looking at anions, they can come from 2 spots. They can either be non-metals that are in the P block, or they can be polyatomics as well. Now, looking at the P block, we follow a very similar principle to what we just looked at for the cations, and that is find the element. So for example, an oxide would be an oxygen atom. So oxide is O. It's got 6 valence electrons, which means the easiest thing for it to do is gain 2 electrons to make 8. If you gain 2 negative electrons, the charge of the anion would be 2 minus. Other examples, if a fluoride had 7, then you could gain 1 electron to make -2. If nitrogen or a nitride had 5 electrons, it could gain 3 more, giving it a charge of -3. There are also lots of polyatomic anions, for example, nitrate, sulfite, or hydroxide. Usually you can tell whether or not an anion is polyatomic by its suffix, ate or ite. Usually P block or elemental polyatomic ions have an ide at the end. There are some exceptions. So for example, hydroxide has IDE at the end. That's a pretty common polyatomic ion, one that you should know pretty quickly. But if you see here, part of its beginning of the name that suffixes, it has the hydrogen part here and the oxygen part here, implying that it's made from 2 different kinds of elements anyway. This is certainly the exception to the rule. Most IDEs are P-block elements. So for example, fluoride, chloride, bromide, iodide, sulfide, nitride, etc. But if we do have a polyatomic ion, again, it's in the table of polyatomic ions and something that is going to be needed to start to be committed to memory. So for example, nitrate is NO3-, sulfite is SO3-2-, and hydroxide is OH-. When you're writing down the formula of ionic substances, there are a few different ways of trying to figure out how to balance the charges. So for example, if I have aluminium oxide, it's going to be made of aluminium, and it's going to be made of an oxygen as well. So aluminium has a charge of 3+, oxide has a charge of 2-. These charges don't balance, so we're going to have to make sure that the aluminium and oxygen in the ionic substance have the right number of cations and anions to ensure that the charges of both the anion and the cation balance each other out, that they exist in a balanced ratio. And there are a few different ways of trying to figure it out. Usually you can do it in your head. Some people like to use this cross method. So if the charge is 3+ here for the cation, then the anion has there will be 3 of them, and if the anion has a charge of -2, then there will be 2 cations. You can also just count up the number of charges and try and figure it out this way. Something that I want to point out though in particular is that if you have a polyatomic ion and there is more than one polyatomic ion that's present in the empirical formula, you need to put it in brackets, because here what this looks like is that there are 32 oxygens in the formula and it doesn't make a lot of sense. The brackets help to space all of those parts out, the cation, the anion, and then the number of each of the particles. These brackets aren't necessary for single or monoatomic ions, for example calcium, or an anion that's elemental like oxygen. They're not needed for that though. Next, I want to look at the formula, writing up a formula for covalent substances. Now, some of them are just common names. So, for example, water doesn't indicate anything about the chemical formula at all, and by memory, we know that this is H2O. There are other examples of these as well, some that you may know already, some that we may learn as we go, but some do have common names, and we just have to know what they are from memory. Some you might be given in a worded problem or a worded equation that just says chlorine gas or some sort of elemental molecule. And so to know how many atoms there are in each, we kind of need to know those by memory as well. Something to keep in mind though is that most gases are diatomic, which means that there are always 2 of them in the molecule. So chlorine gas is Cl2, fluorine gas is F2, bromine gas is Br2, another one might be hydrogen gas is H2. The only exception to this rule really are our noble gases, but they don't really participate in reactive chemistry anyway, so they're not ones that we see very much at all. The other kind, this is probably one of the ones that take the most figuring out, I guess, that aren't memory-based, are inorganic compounds. And so what we can look at is the names of each of the elements that are present. So for example, phosphorus trichloride. So phosphorus is a part of the chemical formula. That's P over here. Trichloride, chloride is Cl. We can find that in the periodic table as well. But because of this tri prefix here, we know that there are 3 of them. Now, because there is no prefix for phosphorus, we just assume that there are 1. But the strategy here is use the periodic table to find the symbols, use the prefixes to find the number of atoms. So the one that's next to it here, dinitrogen pentaoxide. Di meaning 2, there are 2 nitrogens. Penta meaning 5, there are 5 oxygens for pentaoxide. The last kind of covalent compounds, though, we're not really going to be looking at those in these units. They don't come up until Module 7. There is a very complex naming system for all of them, and it's not something that we learn until about this point in Year 12 next year. For now, if we are going to be working with any organic compounds, it can be expected that you'll be given these formulas so that you can write any of these equations, do calculations, balance them, etc. Now, at this point, I want to do a couple of quick practice questions to sort of get you started so that we can do more of these in class.